Hello friend, today in this video I want to discuss group theory. So let's start. At first in the group, the first topic is groupoid. So groupoid, what is groupoid? The definition of groupoid is let G be a non-empty set. Okay, a non-empty set, that means only at least one element is present on the set on which a binary composition. If you don't know about the binary composition, then you can see my first video where I explain the binary composition very well. Binary composition is defined some algebraic structure is imposed on G by the composition, and G composition becomes an algebraic system. The algebraic system G composition is said to be groupoid. So friend, here say the binary composition, that means if Z plus is said to be a groupoid when one element A and another element B belongs to Z. Okay, if after compose, here composition is plus, so after composing A plus B, this is also belongs to Z. One example, 1 belongs to Z, 2 belongs to Z. So 1 plus 2, this is equal to 3 and belongs to Z. When this property is satisfied, then this is called the groupoid. Okay, clear? Similarly, in Q plus, Q is the set of rational number and Z is the set of integer. Here one element A and B belongs to set of rational number Q, so they are adding A plus B, this is also belongs to Q, so Q plus is also groupoid. This is the two example of groupoid. Here we see a note, n minus. Here n is the set of natural number and minus is the binary composition, is not a groupoid. Why? Because 1 and 2 belongs to natural number. Okay, what is natural number? Natural number is 1, 2, 3 ... natural number. 1 and 2 belongs to natural number. Now the composition is minus, so 1 minus 2, this is equal to minus 1. Minus 1 is not belongs to natural number. Okay, because natural number is 1, 2, 3 ... etc. But minus 1 is not belongs to here, so composition is not satisfied, so this is not a groupoid. Okay, now the next topic is semigroup. What is semigroup? A groupoid G composition is said to be a semigroup if composition is associative. Okay, the groupoid is said to be a semigroup when composition is associative. What is associative property? Associative property is A compose B compose C is equal to A compose B compose C for all A, B, C belongs to G. This is the associative property. When the groupoid, that means this groupoid is said to be semigroup when this property is hold. That means A compose B compose C, this is equal to A compose B compose C for all A, B, C belongs to G. Now one example, Z plus is a semigroup. Z plus is a semigroup. Why? Because Here Z plus is a groupoid, so this is Z plus is a groupoid. Okay. Also, if A, B, C belongs to Z, then A compose B compose C is equal to A compose B compose C for all A, B, C belongs to Z. So Z plus is semigroup. This is associative property. Associative property. So this is semigroup. Okay. Another example, Z dot by the composition multiplication. This is also semigroup. 1, 2, 3 belongs to Z. So 1 dot 2 dot 3 is equal to 2 dot 3 is equal to 6, and 1 dot 2 dot 3, this is equal to 1 dot 6, this is equal to 6. Therefore 1 dot 2 dot 3 is equal to 1 dot 2 dot 3. So this is also semigroup. This is groupoid and also associative property hold. So Z dot is a semigroup. This is a particular point of Z. Okay, you may prove this by in general, and here I proved by some particular cases. Also, a note: a semigroup is said to be a commutative semigroup if composition be commutative. That means a semigroup is commutative semigroup when this composition is commutative. Commutative property is A and B belongs to a semigroup G. If A compose B is equal to B compose A, then this is the commutative property, and this is called the commutative semigroup. Monoid: a semigroup G composition containing the identity element is said to be a monoid. Okay, that means a semigroup, here two property involved. Number one, closure property, that means groupoid. Number two, associative property, and number three, the identity element is involved here. And now you say that what is the identity element? So now I say about the identity element. Identity mean if A be an element of G and with a binary composition, A compose E and E compose A, this is equal to A. That means any element E compose with right hand side and any element E compose with left hand side, both are equal to A for all A belongs to G, then this property is identity property and E be the identity element. Identity element. Okay. And another example, a monoid is said to be commutative monoid if composition be commutative. A monoid is commutative monoid if composition be commutative. Example. First example of monoid. Z plus, this is a monoid, because we know Z plus is a semigroup. Okay, Z plus is a semigroup. Now if we proved that Z hold the identity property, then Z is also monoid. Now A belongs to Z, okay, and 0 belongs to Z, okay. A is any arbitrary element, then A plus 0, this is equal to 0 plus A, this equal to A. So 0 is the identity element, so identity property hold. So we say Z plus is a monoid. Similarly, Z dot is a example 2. Z dot is a monoid. Why? A belongs to Z and A dot 1 is equal to 1 dot A is equal to A. Here identity element is 1. 1 is the identity element. So identity property hold, and Z dot is a monoid. Complete. Next, example 3. Zn Zn dot is a monoid. Here Zn is equal to 0 bar, 1 bar, 2 bar, dot dot dot. Okay, which is 1 bar is the identity element. Complete. Now the definition of unit. What is unit? In a monoid, an invertible element is said to be unit. Now you say, what is invertible? The invertible mean A compose A double dash or dash equal to A dash compose A is equal to E. Here A dash is inverse of A and A dash is inverse of A and E is the identity element. Here A dash and E belongs to G being any set, then this property is called invertible property. Okay, if any element of the monoid satisfied this property, then this element is said to be unit. Okay, clear? Any element satisfies this property, this element is said to be unit of monoid. Now one example of monoid. Question is, define a binary composition on the set Z by A compose B is equal to A plus B minus AB for A comma B belongs to Z, then show that Z composition is a monoid. Solution. So closure property. Before showing the monoid, the first is closure property. A and B belongs to Z. So A plus B. So A compose B. This is equal to A plus B minus AB. This is belongs to Z. So closure property hold. Next, associative property. Associative property, that means A, B, C belongs to Z. Now A compose B compose C is equal to A plus B minus AB compose of C is equal to, here the element is A and this is B, so the composition is A plus B minus C, that means first element plus second element minus multiplication of both element. So first element is this A plus B minus AB plus second element is C and minus of both element multiplied A plus B minus AB and multiplication with C. So A plus B minus AB plus C minus AC minus BC plus ABC is equal to A plus B plus C minus AB minus AC minus BC plus ABC. Okay. Similarly, A compose B compose C is equal to A compose A plus B, sorry, A B plus C minus BC. So this is plus first element, this is second element. So A plus first element plus second element, B plus C minus BC and minus of multiplied both element A to B plus C minus BC. This is equal to A plus B plus C minus BC minus AB minus AC minus of plus of ABC and equal to A plus B plus C minus AB minus BC minus CA plus ABC. So A compose B compose of C equal to A compose B compose C for all A, B, C belongs to Z. So associative property hold. Associative property hold. Okay. So two property hold. Number one, closure property, associative property. For monoid, the next property is identity property. Okay. If there exists an element E such that A compose E is equal to E compose A is equal to E. A. This is the identity property. So first, A compose E is equal to A implies A plus E minus AE is equal to A and A are A, both vanish, and E 1 minus A is equal to 0. This is implies E is equal to 0. Similarly, E compose A is equal to A implies E plus A minus EA is equal to A implies E into 1 minus A is equal to 0 implies E is equal to 0. Okay. So 0 is the identity element. 0 is the identity element. And identity property hold. So three property, plus first closure property, second associative property, and third is identity property are hold. So this is a monoid. Therefore Z composition is Z composition is a monoid. Okay, now next example, find the unit and the idempotent element in the monoid Z5 dot. Okay, so solution. The necessary is composition table. The table is with respect to multiplication. Here this is the Z5 element, 0 bar, 1 bar, 2 bar, 3 bar, 4 bar, and here 0 bar, 1 bar, 2 bar, 3 bar, 4 bar, and multiplication is binary composition, 0 0 0 0 1 0, so all 0, 0 0 0 0 1 0, so all 0, 1 0 0 1 1 1 1 2 2 1 3 3 and 1 4 4. Okay, 2 1 2 2 2 4 2 3 1. How this is 1? 2 and 3, 2.3, this is equal to 6. Okay, and here modulo 5, that means when we divide by 5 the remainder term is 1, and this is written here. 4 to 3, 4 to 8, so 8 is divisible by 5, then the remainder is 3. 3 4 12, and when 12 is divisible by 5, then remainder is 2. So the composition table is complete. Now the question is find the unit, and in this video you know that what is unit. In a monoid the invertible element is said to be unit. So what is the invertible element that has inverse? Now at first the identity element in Z5, we know in Zn the identity element is 1 bar, so inverse of 1 bar is 1. Why? In table 1 bar, and this is the identity element, so 1 is the identity element inverse of 1. Okay, inverse of 2 bar is 2 bar. Here identity element 1, so inverse of 2 bar is 3 bar. Inverse of 3 bar is 3 bar. Here identity element, so 2 bar. Inverse of 4 bar is here identity element, so this is inverse 4 bar. Okay, so the unit element is 1 bar, 2 bar, 3 bar, 4 bar, that has unique inverse. Next, the idempotent element. Before finding the idempotent element, the necessary is idempotent. Idempotent mean A compose A is equal to A. This is idempotent, that is A square is equal to A. Okay, so 0 square is equal to 0, so this is idempotent. 1 square is equal to 1, so this is also idempotent. 2 square is equal to 4, so not idempotent. 3 square is equal to 9, but divisible by 5, so this is equal to also 4. This is not idempotent. And 4 square is equal to 16, divisible by 5 is equal to 1, so this is also not idempotent. The idempotent element is this 0 and 1, therefore idempotent element is in Z5 is 0 bar and 1 bar. Okay, complete.